In most jurisdictions, homeowners can secure permits for electrical projects if they own the property and do the work themselves. They generally cannot hire licensed electricians to perform the work under their permit. It's important to check with the local building department to determine the specific permit requirements for electrical upgrades. Most jurisdictions mandate inspections for major electrical work, especially panel upgrades. If you find yourself regularly performing this type of work, you may need to apply for a contractor's license. Beyond just upgrading the feeder wire and installing arc fault breakers, you might also need to improve the grounding system and add new circuits if the existing ones cannot handle the increased demand. Always ensure the upgrade adheres to all applicable electrical codes and standards. Prioritize safety during the installation. Wear appropriate personal protective equipment and follow lockout/tagout procedures. During the inspection, expect the inspector to verify several key aspects. Firstly, the correct sizing of the feeder wire and circuit breakers. Secondly, the proper installation of the new panel. Thirdly, an upgraded grounding system, if one was required. Fourthly, adequate circuit protection for the increased load. And fifthly, any other applicable code requirements. It's recommended to contact the local building department to get specific permit information and application forms. Familiarize yourself with the governing electrical codes and standards. If you are not entirely confident in completing the work, consider collaborating with a licensed electrician for guidance. Document your work thoroughly, including photographs and notes on any deviations from the original plan. Proceed cautiously and make sure all work is performed safely and in accordance with applicable regulations. When upgrading an electrical service from 100 amps to 200 amps, several key considerations and steps are involved, going beyond simply replacing the panel and increasing the feeder wire size. A comprehensive approach ensures safety, code compliance, and long-term reliability. Firstly, conduct a load calculation. A crucial initial step is to perform a detailed load calculation according to the National Electrical Code, or NEC. This calculation determines the actual electrical demand of the home, considering all existing and planned appliances, lighting, and equipment. The load calculation ensures that the new 200 amp service is adequately sized to handle the anticipated load, preventing overloads and potential hazards. NEC Article 220 provides the guidelines for performing these calculations. Secondly, upgrade the service entrance conductors. The service entrance conductors, which run from the utility company's connection point to the main service panel, must be upgraded to handle the increased amperage. The size of these conductors is determined by the ampacity requirements specified in NEC Table 310.16 based on the conductor material, insulation type, and installation method. Ensure the conductors are properly rated for the 200 amp service to avoid overheating and voltage drop. Thirdly, replace the meter socket. The meter socket, which houses the electric meter, may need to be replaced to accommodate the 200 amp service. Check with the local utility company for their specific requirements and approved meter socket types. The new meter socket must be rated for 200 amps and be compatible with the utility's metering equipment. Fourthly, upgrade the grounding system. An essential part of any electrical service upgrade is ensuring a robust and compliant grounding system. This typically involves upgrading the grounding electrode conductor, which connects the neutral busbar in the service panel to the grounding electrode system, such as ground rods or a metallic water pipe. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. Additionally, ensure that all metallic components such as water pipes and gas pipes are properly bonded to the grounding system to minimize the risk of electric shock. Fifthly, install a new service panel. Replacing the existing 100 amp panel with a new 200 amp panel is a central part of the upgrade. The new panel should be UL listed and labeled for use as service equipment. It must have sufficient overcurrent protection devices, such as circuit breakers, to protect all the branch circuits in the home. When selecting the new panel, consider factors such as the number of available spaces for breakers, the type of breakers required, and any additional features, such as surge protection. Sixthly, install arc fault circuit interrupters, or size and ground fault circuit interrupters, or GFCIs. As you mentioned, installing arc fault circuit interrupters, or size, is essential for protecting against arc faults, which can cause fires. SIs are required for branch circuits that supply bedrooms, living rooms, and other areas specified in NEC 210.12. Similarly, ground fault circuit interrupters, or GFCIs, are required for circuits that serve bathrooms, kitchens, and outdoor areas, as specified in NEC 210.8 to protect against electric shock. Ensure that the new panel is equipped with the appropriate size and GFCIs to meet code requirements. Seventhly, inspect and upgrade branch circuits. While upgrading the service panel, it's an opportune time to inspect the existing branch circuits to ensure they are in good condition and properly sized for their intended loads. Look for any signs of damage, such as frayed insulation or loose connections. If necessary, upgrade any undersized or damaged branch circuits to meet current code requirements. This may involve replacing the wiring and installing new outlets or fixtures. Eighthly, label circuits clearly. Proper labeling of circuits is crucial for safety and convenience. Clearly label each circuit breaker in the new panel to indicate the area or appliance it serves. Use a circuit directory or label maker to create clear and accurate labels. This will make it easier to identify and troubleshoot circuits in the future. Ninthly, obtain necessary permits and inspections. Before starting the upgrade, obtain the necessary permits from the local building department. The permit process typically involves submitting a detailed plan of the proposed work and paying a fee. Once the upgrade is complete, schedule an inspection with the building department to ensure that the work meets code requirements. The inspector will verify that the service entrance conductors, grounding system, panel installation, and other aspects of the upgrade comply with the NEC and local codes. Tenthly, document the work. Keep detailed records of all work performed, including the load calculation, conductor sizes, panel specifications, and inspection results. This documentation will be valuable for future reference and may be required for insurance purposes or when selling the home. Take photographs of the installation process to document the work and identify any potential issues. In summary, upgrading an electrical service from 100 amps to 200 amps involves a comprehensive approach that includes load calculations, service entrance conductor upgrades, meter socket replacement, grounding system improvements, panel replacement, SI and GFCI installation, branch circuit inspection, circuit labeling, permit acquisition, inspection scheduling, and thorough documentation. By following these steps and adhering to code requirements, you can ensure a safe, reliable, and compliant electrical service upgrade. Let's delve deeper into some of the specific aspects of upgrading an electrical service. Firstly, understanding load calculations. NEC Article 220 provides the guidelines for calculating electrical loads in residential, commercial, and industrial buildings. The purpose of a load calculation is to determine the minimum size of the electrical service, feeders, and branch circuits required to safely and adequately serve the connected loads. There are two main methods for calculating loads: firstly, the standard method, and secondly, the optional method. The standard method is more detailed and is typically used for larger or more complex installations. The optional method is simpler and is often used for single-family dwellings. Key factors in load calculations include general lighting loads, small appliance branch circuits, laundry branch circuits, individual appliance loads, heating and air conditioning loads, and electric vehicle charging equipment loads. Specific demand factors are applied to these loads based on the type and number of connected devices. Secondly, selecting the right conductors. NEC Table 310.16 provides the ampacity ratings for various types of conductors based on their material, insulation type, and installation method. The ampacity of a conductor is the maximum current it can safely carry without exceeding its temperature rating. When selecting conductors for an electrical service upgrade, it's essential to consider the ampacity requirements, voltage drop, and environmental conditions. Copper conductors are generally preferred for their higher conductivity and corrosion resistance, but aluminum conductors may be used for larger sizes to reduce cost. The insulation type must be suitable for the operating temperature and environmental conditions such as moisture and exposure to chemicals. Voltage drop, which is the reduction in voltage along a conductor due to its resistance, must be kept within acceptable limits to ensure proper operation of equipment. NEC 210.19 and 215.2 provide guidelines for minimizing voltage drop in branch circuits and feeders. Thirdly, grounding and bonding requirements. NEC Article 250 provides the requirements for grounding and bonding electrical systems. Grounding is the process of connecting the neutral conductor to the earth to provide a low impedance path for fault current. Bonding is the process of connecting all metallic components to the grounding system to minimize the risk of electric shock. The grounding electrode system typically consists of one or more ground rods, a metallic water pipe, or a concrete encased electrode. The grounding electrode conductor connects the neutral busbar in the service panel to the grounding electrode system. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. Bonding is achieved by connecting all metallic components such as water pipes, gas pipes, and metal enclosures to the grounded system using bonding jumpers. NEC 250.92 and 250.96 provide the requirements for bonding metallic components. Fourthly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. Circuit breakers are resettable devices that automatically trip when an overcurrent condition occurs. Fuses are one-time devices that melt and open the circuit when an overcurrent condition occurs. The size of the overcurrent protection device must be matched to the ampacity of the conductor it protects. NEC 240.4 provides the rules for selecting overcurrent protection devices. A size are required for branch circuits that supply bedrooms, living rooms, and other areas specified in NEC 210.12 to protect against arc faults, which can cause fires. GFCIs are required for circuits that serve bathrooms, kitchens, and outdoor areas, as specified in NEC 210.8 to protect against electric shock. Fifthly, surge protection. Surge protection devices, or SPGs, are used to protect electrical equipment from voltage surges caused by lightning, utility switching, and other events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are available in various types and sizes, including whole-house SPD that are installed at the service panel and plug-in SPD that are used at individual outlets. NEC 230.67 provides the requirements for surge protection in dwelling unit. It's recommended to install a whole-house SPD to protect the entire electrical system from voltage surges. Sixthly, electrical inspections. Electrical inspections are conducted by local building departments to ensure that electrical installations comply with the NEC and local codes. The inspection process typically involves submitting a permit application, paying a fee, and scheduling an inspection after the work is complete. The inspector will verify that the service entrance conductors, grounding system, panel installation, and other aspects of the electrical system comply with code requirements. Any deficiencies identified during the inspection must be corrected before the installation can be approved. It's important to cooperate with the inspector and provide any documentation or information they request. Seventhly, working with the utility company. Before upgrading an electrical service, it's essential to coordinate with the local utility company. The utility company may have specific requirements for the service entrance conductors, meter socket, and other equipment. They may also need to upgrade their equipment to accommodate the increased load. Contact the utility company early in the planning process to discuss the proposed upgrade and obtain any necessary approvals or permits. Eighthly, safety precautions. Working with electricity can be dangerous, so it's essential to take appropriate safety precautions to minimize the risk of electric shock and other hazards. Always to energize circuits before working on them using lockout/tagout procedures to prevent accidental re-energization. Wear appropriate personal protective equipment, or PPE, such as rubber gloves, safety glasses, and arc-rated clothing. Use insulated tools and equipment to prevent electrical shock. Avoid working in wet or damp conditions. If you're not comfortable working with electricity, hire a qualified electrician to perform the work. In summary, upgrading an electrical service requires careful planning, attention to detail, and adherence to code requirements. By understanding the key aspects of the upgrade, such as load calculations, conductor selection, grounding and bonding, overcurrent protection, surge protection, electrical inspections, utility coordination, and safety precautions, you can ensure a safe, reliable, and compliant electrical installation. Remember to always consult the NEC and local codes for specific requirements and to hire a qualified electrician if you're not comfortable performing the work yourself.